Greetings to all and welcome to this lecture. We are in module 5, lecture number 1. In this lecture, we will discuss about the body effect, means how the body of 2-terminal or 3-terminal structure affects your inversion charge, or in general the surface charge. We will see few reasons of operation, mainly the strong and the weak. These are the learning outcomes of this lecture, which helps us to understand thoroughly about the impact of VCB in your channel charge. Let us do a quick recap. We were discussing about the 3-terminal MOS structure, and we said that the inversion charge which is present here near the surface can be altered by applying voltage at C to B, meaning a new terminal C or contact actually modulates your inversion charge externally. However, in 2-terminal MOS structure, your VGB was the sole voltage or sole contributor to get this inversion charge, and the inversion charge was only coming from deep body. However, in 3-terminal MOS structure, we see that the influence of VCB is significant when you are talking about the inversion charge. We have derived all those equations what we have also derived for 2-terminal structure, considering that N naught can be replaced by N naught into e to the power of minus VCB divided by phi t, meaning the VCB voltage influences your inversion charge, and the surface potential, instead of writing 2 phi f, it should write with 2 phi f plus VCB, meaning the required gate voltage is such that the increase in psi s, which is surface potential, will not fight only against 2 phi f, it should fight against 2 phi f plus VCB to get the same amount of inversion under the influence of VCB. We have also derived few of the equations in different region of operations like inversion. So, this is total charge equation for inversion and depletion. This is the charge equation for inversion, and we related that charge equation with external voltages, which is nothing but VGB. You can see here the closed form equation will give you the influence of both VGB and VCB on your surface potential. We also derived the capacitance equations for bulk charge and the inversion charge by taking appropriate differentiation, meaning CB dash is equals to minus of delta QB dash divided by delta psi s, and CI dash was given by minus of delta QI dash by delta psi s. We argued that the VCB voltage will not affect your depletion charge, but it will affect the change in the depletion charge, and hence the VCB term is coming in your CB dash equation. Today, let us start about discussing this 3-terminal structure in a different aspect, meaning we said that we have body as a reference. Whatever be the voltage we are applying with respect to body. Here this voltage is called as VGB, means gate to body voltage. Similarly, this voltage is called as VCB, means C to body voltage. Can we replace this connection by a new connection like this? Instead of making body as a reference for gate voltage, I can make C as a reference for gate voltage. This means same because the overall voltage between gate to body, which is VGB, is nothing but VGC plus VCB. Here the reference is changed, but the overall impact will be same, but changing the reference will give you a new understanding of this 3-terminal MOS structure. The influence of VCB here is solely captured the change in the charge in the surface with constant VGC, and ultimately this is called body effect. Let's explore this in more detail. So ultimately the body effect is the effect which says that how VCB controls your charge in the surface, right, for a constant value of VGC. Let me redraw that structure, which says that we have N plus here, and here you have same as two terminal structure. So this is gate, this is VCB, this is body terminal, and this is VCB. Instead of applying gate to body voltage, we are applying VGC. Once we apply VGC, we will see the influence of VCB. What will happen if you apply VGC for a particular value, VGC for a particular value, you are in inversion, let's say, and when you increase VCB, the inversion gets lightened up, right? Because of that, VCB controls your surface charge. Let's take an example. Let us consider you applied VGC of some amount which gives 100 unit of charge, 100 units of positive charge at the gate, which is generally we termed it as QG dash, correct? Now you are keeping VCB constant now, and you applied VGC in such a way that you are in strong inversion. So there is depletion region and there is inversion charge. 100 positive charge requires 100 negative charge at the surface, because this forms a parallel plate capacitor with COX dash coming into picture, right? Here this is a dielectric layer which is silicon dioxide made up of thickness TOX, correct? Now what will happen if you keep VGC constant to that value and now you increase VCB? The moment you increase VCB, let me change the color of my pen. If you change VCB, ultimately the depletion region here will increase, because you are making this N plus P junction as reverse bias. So the depletion region gets expand. If the depletion region get expand, the charge balancing occur here. Now earlier, let's say the inversion charge was minus 90 unit and depletion charge was minus 10 units. But now when you increase VCB, you reverse bias it, and hence more depletion charge will come into picture. This depletion charge, let us consider, now they become 40. So if the 40 minus charge is governed or captured by depletion region, the inversion charge needs to be reduced to minus 60, because here your gate to channel or gate to C VGC voltage is fixed. It means you cannot change QG dash. If VGC is fixed, QG dash is fixed, and hence the capacitance here will be fixed. So the overall charge balancing says if this minus 40 unit is depletion charge, then minus 60 will be your inversion charge. Now if you further increase VCB, what will happen? Further, the extension of depletion region occur. The depletion region expanded further, and hence the contribution of depletion charge to make a charge balance here, it will increase. Let's say now the depletion charge become minus 90. So ultimately the inversion charge is reduced down from minus 90 to minus 10, right? Here don't consider minus as a minus of number. It is minus means the negative of charge. It is negative charge, right? So ultimately the count of inversion region, the count of inversion layer is reduced and the count of depletion charge will increase. So that is what, if you increase VCB, then your structure will move from strong inversion to moderate inversion to weak, and ultimately you will ended up with depletion. So for a fixed VGC, the increase in VCB controls your channel charge. That is nothing but a body effect. This VGB can be written as VGC plus VCB. So now when you increase VCB, right, there is obviously a chance that VGB increase, but where this VGB increase goes? Ultimately the increase in VGB is actually increases towards the depletion region, which makes the charge balance. Now if you want the same amount of inversion again to attain, then you need to increase VGB such that the surface potential increases in that amount so that the inversion becomes same. Make sure the increase in VGB should be larger than increase in VCB, because the VGB will drop across the oxide also. So as we have already discussed, VCB is directly influencing your surface potential. That's what we have seen, that the onset of points, the onset points will increase, like from 5F it becomes 5F plus VCB, from 2-5F it becomes 2-5F plus VCB. But when you are increasing VGB, ultimately the increase in voltage will drop across the oxide also, and hence the increase in VGB which will be more as compared to the increase in VCB. You can simply say the increase in VGB should be in such a way that it should increase the surface potential by the same amount of VCB. Correct? This is ultimately called a body effect. Now what will happen if the body doping will increase? So I am increasing the body doping. If I increase the body doping, based on the applied voltage of VCB, more number of depletion charge will get changed. Because of more depletion charge change, the inversion region will decrease, and hence the doping of the body is actually influencing what amount of gate voltage is required to get the same amount of inversion. Ultimately you can say the gate voltage, the requirement of gate voltage is increased if the doping concentration increases. The other aspect of the structure is oxide thickness. If I increase the oxide thickness, means I am making a weak control of this gate, and hence the influence of VCB will be more. So the body parameters like doping and the oxide thickness is actually influencing your charge under the influence of VCB. This whole sum is called body effect, which can be given by body effect coefficient, which we have already discussed thoroughly. In many of the places we have used this, and it is given by 2 into Q into Na into epsilon S divided by COX prime. If you see here, the Na, which is body doping, and this can be written as square root of 2 into Q into Na into epsilon S divided by epsilon OX dash into TOX, and it depends upon the oxide thickness. So ultimately if you increase the oxide thickness, you are actually making a weak control of the gate voltage, and hence you need to require more gate voltage to get the same inversion which was killed by VCB. So to restore the inversion, the VGC should be increased. That's what we have already discussed, as VGB is equals to VGC plus VCB. So the increment in VGB which will be higher than VCB. Let's see different reasons of inversion. We have said that when we increase VCB, ultimately your channel charge goes from strong inversion to moderate inversion to weak inversion and all. Ultimately the increase in VCB weakens your strong inversion. So we can say earlier in 2-terminal MOS, 5F was the onset of weak inversion, 2-5F was the onset of moderate inversion, and 2-5F plus phi Z0 or delta 5F is equals to onset of strong inversion. That what we have discussed earlier. But now when you introduce VCB in your structure, ultimately the onset of these values will get shifted in surface potential. So ultimately the surface potential requires 2 phi f plus VCB, which is onset of moderate inversion, 2 phi f plus phi z0 plus VCB as an onset of strong inversion, and 2 phi f plus VCB as an onset of weak inversion. So now can we rewrite these equations using our potential balance equation such that we can find out what amount of gate voltage we should require to get these onset points. So we know from our potential balance equation that VGB is equals to V flat band voltage plus psi s plus gamma root psi s. We have derived this equation in many places. So here when VCB is coming into picture, that the surface potential or the onset point is get changed. So VGB corresponding to which when my onset of weak inversion occur, right, this is defined as VLB. Earlier if you remember, we defined VLO, which we said that VLO is the value of gate to body voltage when surface potential is equals to phi f. Similarly, we defined VMO as gate to body voltage when surface potential is 2 phi f. But now the surface potential is phi f plus VCB to get the onset of weak inversion. Similarly, surface potential should be 2 phi f plus VCB to get the onset of moderate inversion, and so on and so forth. Now we are defining another word with respect to LB or with respect to B, because now we have two supplies, VCB and VGB. So to get differentiate meaning, we defined a new term which is VLB, where we need to take the onset of weak inversion under the influence of VCB, which is nothing but what, phi f plus VCB. Let's use this equation to calculate what is VLB. So VLB would be V flat band voltage plus psi s. Now when VCB is applied, then phi f plus VCB is your what, the onset of weak inversion. So surface potential should be given by phi f plus VCB, right, plus gamma times of phi f plus VCB. This will give you the value of VLB. Similarly, we can find out VMB, which is written here, which is nothing but V flat band voltage plus the surface potential value under the influence of VCB. Now it becomes 2 phi f plus VCB plus gamma times 2 phi f plus VCB. Again, these values are reference to the body terminal, meaning you are measuring the gate voltage with respect to body. This is what VGB is. But we just saw that instead of writing VGB, I can split and make this C terminal as common. So instead of writing VGB, I can simply write VGC and VCB. So this notation gives you what is the gate voltage with respect to this C terminal, correct? So VGB is equals to VGC plus VCB. If I subtract VCB from the values of VGB, I will get all the values in reference to C. That is what we are going to do here. We are actually subtracting the VC value from VLB. So all these equations will be in the form of VLC or VMC. To avoid these confusions, we simply denoted a new term VM or VL or VH or VT. right? Will come in next slide, these values will come up. So it's clear that when you are measuring the voltage with respect to C terminal, then these quantities can be referenced as Vm, Vl, Vt, etc. So here Vm is nothing but Vm minus Vcb. So ultimately you are subtracting this Vcb there, ultimately this will give you the value of Vm. Now if I plot this graph here, if I plot this graph with respect to Vcb, you can see if Vcb is equals to 0, ultimately you are in the case which is considered in two terminal MOSFET, right? And hence there we define few values which is as VLO, VMO, VTO and VHO, which we said that this is onset of weak inversion, onset of moderate inversion, extrapolated threshold voltage, and this is nothing but onset of strong inversion. But now when you increase Vcb, as we just saw that Vm is equals to V flat band voltage plus 2 phi f plus gamma times of 2 phi f plus Vcb. It means Vm does have Vcb dependency. So if you increase Vcb, the Vm will increase. So that is what, if you are increasing Vcb, the Vm will increase and attain a value of Vm, which can be intuitively understood like when you are increasing Vcb, ultimately you are killing the inversion charge, and hence you need to apply much more voltage in terms of VGC to get the same amount of inversion. So ultimately the threshold value, the onset of a weak inversion, the onset of moderate inversion will get shift to a higher value. That is what it means is. Now let's explore in much more detail about strong inversion. In general, the strong inversion can be classified as when the inversion charge is much more higher than the bulk charge. This is what we called as a strong inversion. If we remember, you remember that we have also plotted the charge versus surface potential plot, and we said that till 2 phi f this charge was bulk charge. So this is phi f, this is 2 phi f. Just around phi f, this Qi approaches to a very high value because of exponential dependency. Correct? But this is not the accurate approach to find out the strong inversion, because the slope we require to get whether this charge are linear at this point or not, the charge voltage relation is linear or not. That is what we define, that instead of taking charge, we will take the capacitances. Meaning if Ci dash is greater than Cb dash, we can simply say that we are in strong inversion, right? This point, strong inversion, is calculated as surface potential is equals to phi naught plus Vcb, because as we just discussed, all the points will get shifted to the right, meaning will shifted by the Vcb. So when I am talking about the surface potential required for causing a strong inversion, then surface potential should be equal to phi naught plus Vcb, where phi naught is nothing but 2 phi f plus delta phi, or you can write phi z0 plus Vcb. If you take the change in the surface potential with a change in the Vcb in strong inversion, then what we'll get? The change in the surface potential is almost same as the change in Vcb, or you can say delta psi s by delta Vcb plot is almost linear. This holds good when you are in strong inversion. We will see this aspect. So in strong inversion, what will happen to the depletion region? The depletion region gets its maximum depth, and hence we can rewrite dB max at strong inversion. We can use these equations again, as we have already frequently used these equations to find out the inversion charge in respect to VGB. So by using these equations and solving the potential balance equation, ultimately will ended up Qi dash is equals to minus of Cox dash into VGB minus VTB, where VTB is nothing but V flat band voltage plus surface potential plus gamma times of surface potential. So, as you are talking about extrapolated threshold voltage with respect to body, then surface potential at that moment is what? Phi naught plus VCB. So, ultimately VTB can be given as V flat band voltage plus phi naught plus VCB plus gamma times of square root of phi naught plus VCB. Now, if I want to represent with respect to C as a common terminal, I need to simply subtract VCB from here. This will give me a new value which is Vt, which is called threshold. So, Vt can be given by V flat band voltage plus phi naught plus gamma times of phi naught plus VCB, right. And here also this VGB can be replaced as VGC plus VCB, and this VTB can be replaced as VCB plus VT. So, ultimately when you put that, you will get a closed form equation as VGC minus VT. This is called overdrive voltage. We will discuss in much more detail when we will go for MOS transistor. So, Vt, and there is another term we can define as Vt naught when VCB is equals to 0. So, this is just a mathematical interpretation to understand what is the influence of VCB on threshold voltage. So, we are keeping VCB 0 here. If VCB is equals to 0, that Vt is defined as Vt naught, and we plotted here Vt minus Vt naught with respect to VCB. If we simply analyze this graph, this says that when you increase VCB, then the level of inversion at your surface decreases, and hence you need to apply more gate voltage to increase the level of inversion, which means the threshold voltage will increase. So, that is what the threshold voltage is increasing when you increase VCB towards the X or towards this direction. But this is the influence of gamma, as what we have already discussed. Gamma is nothing but square root of 2 into Q into Na into epsilon S divided by COX dash, or you can rewrite as epsilon ox into Tox. So, ultimately when the body factors comes into picture, the threshold voltage is again increasing. If Tox will be high, you need to have more gate voltage. If Na will be high, you need to apply more gate voltage to get the same amount of inversion. So, ultimately this graph shows the influence of Na, Tox and VCB on your threshold voltage of the device. Now, let us understand the weak inversion. The influence of VCB will be significant in weak inversion as well, though. So, total channel charge can be written as minus of 2 into Q into Na into epsilon S into psi s plus e to the power of psi s minus 2 phi f plus VCB over phi t. This is the total channel charge, and based on the value of surface potential, it will be decided that whether you are in weak inversion or strong inversion. Let us consider that you are in weak inversion. Under weak inversion, what will happen? The surface potential now will be less than 2 phi f plus VCB, and it would be greater than phi f plus VCB. You remember we discussed this kind of analysis on weak inversion when we said that surface potential will be less than 2 phi f and greater than phi f. Under this condition, this factor, so there will be a phi t also, this factor is always smaller than psi s. So, let us consider this factor as zeta, and we can rewrite the inversion charge equation as minus of 2 into Q into Na into epsilon S into square root of psi s plus zeta minus you have bulk charge Qb dash, because Qi dash is nothing but Qc dash minus Qb dash, and the bulk charge is given by minus of 2 into q into Na into epsilon s square root of psi s. If you rewrite this equation, you will get inversion charge as minus 2 into q into Na into epsilon s psi s plus zeta minus root psi s. Use Taylor series expansion considering zeta is very small than psi s. Ultimately, you will get root psi s plus zeta divided by 2 root psi s minus root psi s, and you see that this factor will get cancelled, and ultimately you will left with the equation of inversion charge, which is nothing but minus of 2 into q into Na into epsilon s divided by 2 times of psi s into zeta. Zeta is nothing but phi t e to the power of psi s minus 2 phi f plus Vcb over phi t. Again, as we know that in weak inversion, the surface potential is having some fixed value, because this is nothing but same as the surface potential of depletion condition, which was characterized as psi sa. This is given by this equation, and we have already discussed that under weak inversion the total surface potential is given by this equation. So we can replace this surface potential here by psi sa. Interesting to see here that you have two components. One is dependent on Vgb, so psi sa is a Vgb function, and one is Vcb dependence. You just bifurcate this equation and you will get here. So this will give you the dependent function on Vgb, and this is a dependent function on Vcb. It means the influence of Vcb is clearly visible in your weak inversion region also, meaning in weak inversion you do have some amount of inversion charge and the depletion charge. So when you increase Vcb, ultimately the inversion charge is exponentially decaying out, correct? So let's further simplify this equation by our well known plot between psi s and Vgb. We know that when we plot the surface potential versus Vgb, we got almost linear graph till the value of 2 phi f. So these are the onset points which was defined earlier in two terminal MOS, where we said that this is the onset of weak inversion and this is the onset of moderate inversion. Till this point the surface potential is almost linear, and we have also calculated the slope factor as d psi a by dVgb, and after this point this surface potential is deviate and gets pinned to a value, to a fixed value. We are using the same approach, but make sure here the scale will get changed, because you have included Vcb, and hence these new onset values will be changed to 2 phi f plus Vcb and phi f plus Vcb, correct? So when you do that, you will need to simplify this equation by considering the psi sa value. We have already discussed that factor, where I should replace the psi sa by this value, considering exactly at this point, exactly at the onset point, though the slope get deviates, but we are considering that this slope is linear, and we define that slope n as delta psi by delta Vgb psi sa inverse, and we got the value also. This will give you 1 plus gamma divided by 2 times of root psi sa, right? So this will give you the slope factor. Based on that, what we said is exactly at this point the psi sa can be replaced by 2 phi f plus Vcb, but you need to take care while taking good amount of approximation that if I replace the psi sa in the exponent, it is highly sensitive. So you cannot replace psi sa by this fixed value of 2 phi f plus Vcb, whereas when you write this equation, the psi sa is coming in the denominator also, and this quantity 1 over root psi sa is not much more sensitive. We have seen one example also when we were discussing in two terminal MOS. If let us consider psi sa value is 0.7, then 1 over root psi sa will give you around 1.19, and when psi SA or the surface potential value is 0.8, then this value will give you around 1.11. So the sensitivity of that factor is very small, and hence you can simplify it by replacing psi SA by 2 phi f plus VCB. Again, using the same approach, we will define the inversion charge with respect to the applied voltages. So we followed the same approach to calculate the slope. At this point, this value is 2 phi f plus VCB, and correspondingly this value is defined as VMB when you are plotting with respect to gate to body voltage. Again, here you are measuring your gate voltage with respect to body terminal. So if I am considering this slope is almost linear, I can simply write psi SA, which is function of VGB, minus 2 phi f plus VCB, it can be equal to 1 over n into VGB minus VMB. I can simply replace this in our charge equation, where I will get Qi dash is equals to minus of 2 into Q into Na into epsilon s divided by 2 times of 2 phi f plus VCB into e to the power VGB minus VMB over n times of phi t. This is same as what we discussed in 2 terminal MOS. This can again simplified as, for VGB value is equals to VMB, will get this factor to be 1, and hence we can rewrite as Qi dash is equals to Qm dash or Qm dash into e to the power of VGB minus VMB over n times of phi t. Correct? This can further simplify it, because we have already discussed that instead of taking body as a reference, I can take C or the contact as a reference. So we know that VGB can be written as VGC plus VCB. Similarly, VMB can be written as VM. We have defined that word VM plus VCB. So if we put here, we will get ultimately a closed form equation which says that how my inversion charge is related with the gate voltage. So Qi dash is equals to Qm dash into e to the power of VGC minus Vm by n times of phi t. This tells us how my gate charge is related to gate voltage. So let me summarize this lecture, where we have discussed thoroughly about body factor or body effect. We said that the substrate doping Na and the oxide thickness plays a crucial role while deciding your channel charge, or ultimately it requires the more amount of gate voltage should be required to causes the same amount of inversion. We have also seen what is the influence of VCB in your weak inversion and strong inversion. We defined different values with respect to gate to body voltage and contact to body voltage, or VCB and VGB. We have also defined the threshold voltage value with respect to gate to contact voltage, and we found that when you increase VCB, ultimately the points will get shifted upward, meaning the threshold voltage will shift upward. You require more gate voltage to get the same amount of inversion when VCB will come into picture. So we will stop here for today. Until then, take care.